Okay, so let's go ahead and jump into hyperbolic trig functions. And I thought I'd start this with some graphs. So as we know, when you take your standard sine function, there you go in purple, the sine function when it's first introduced in pre-cal, it's usually introduced using either the unit circle, or you might start with the right triangle and you learn, sine is opposite over hypotenuse, blah, blah, blah. But the whole idea behind the trig functions from pre-cal is that they are all connected to the unit circle, and they generate these very nice curves. We've got that, we've got a cosine x, we've got tangent of x, right? So we've got all these curves that are all somewhat connected to the circle or right triangle. Now, the new 6 trig functions that we're going to learn today are called the hyperbolic functions. These functions actually don't come from the unit circle. Well, they kind of do, but the way we're going to look at them, we're just going to act like they're completely unrelated. What they actually come from is another function that you studied in college algebra, the natural exponential function, which is e to the x. And here it is. Here's e to the x graphed for us. And there's something about this function that's very special. Let's see if we can talk about what makes this function so great. So let's say I were to go to some arbitrary x value. Let's say I go to the x value of 1. I don't like that color. Okay, let's say we go to the x value of 1, and we plug that into the function e to the x, right? That's the function we're looking at, y equals e to the x. And when we plug that in, we're going to get some value. It's going to be like 2.7 something, right? So great. You could do that with any function. You take an x value, plug it in, you get an output, right? But what is it about the exponential function? Can somebody tell me that makes it just so special to us? It has a property.
It doesn't touch 0 on the x-axis?
Okay, so it has a horizontal asymptote. It doesn't touch the x-axis ever. That is a property of it, but it's not unique. There are other functions that do the same thing. In fact, if I were to graph the function 2 raised to the x, there's 2 to the x, that also doesn't touch the x-axis. So although that is a property, it is not the property that makes it just so damn special. Like 2 to the x is special, but it's not as special as e to the x. So this has to do with something. There's 4 to the x if you want 4 to the x. Go ahead.
Does it always go through the 0.1?
Okay, so that all exponential functions of the form a to the x will go through the 0.01. Again, that is a property of it, but it's not what makes it just so unique. It has something to do with Cal 1. I'm asking this question because I'm wondering how much this is emphasized. How much was it emphasized in Cal 1?
It's its own derivative?
Okay, that's it. This function is its own derivative. Now, what does that mean? That means that if I were to go to this x value 1, right, and I were to go up to this point, and I were to look at the tangent line there, okay, so imagine we have a tangent line to that curve right there. The slope of that would also be e to the 1. So it would also be 2.71. This function has the unique property that the slope of the tangent line at any point on the curve is actually equal to the y value of the function. Well, to the y value of that curve. No other function behaves that way. None. All right? Any other function that you ever come up with, you will never have this property happen. So as a kind of illustration, let's say we take the function x squared. Okay? If we were to go to 1, okay, and plug that in, we get a point here. We do the tangent line here. Well, first of all, what's the y value there? So we plug in 1 into x squared. spits out 1, okay? Is that what the slope of the tangent line is there? Well,
No.
what's the derivative of x squared?
2x.
2x. Now, if we plug 1 into that, what do we get?
2.
2. So the slope of the tangent line here is 2, which is definitely not equal to 1, right? So the slope of the tangent line at that point is not equal to the y value of the point. E to the x is the only function out there that has that property. So that's what makes it so special to us. Oops, I'm hitting the wrong button here. Okay,
So is it just e to the x or any number to the x?
just e to the x.
Just e to the x? Okay.
Just e to the x. Good question. So like if we were to take the function 2 to the x, right, and take its derivative, the derivative of 2 to the x would be 2 to the x times natural log of 2. I'm using this property from Cal 1 that the derivative of a to the x is a to the x times natural log of a. So if you were to do, let's put 2 to the x back up here. Okay, this blue one here, if we were to plug 1 in to this function, go up here, the y value would be 2 to the 1, which is 2. But if we get the slope of the tangent line there, we would have to plug 1 into this, and that would give us that the slope is 2 times natural log 2, which is not 2. It's a little bit off.
Okay.
Okay. So historically, it actually worked backwards. We didn't like have the exponential function e to the x. We didn't like have it and then said, oh, great, look at this great property. We actually were like, it would be wonderful if we had a function that had this property, and then we went looking for it, and we actually determined that this is it. Like we knew what we wanted, and then we actually went and discovered it. Now, I will do a little disclaimer. There is another function that behaves, that has this property, but the function is y equals 0, or f of x equals 0. That function, when you take its, like just if we graph it, right, it's kind of a very boring function. If we graph 0, I don't even know if I can graph 0. Y equals 0, oh, 0, there we go. It's just this flat line. And so the y value is always 0, and the slope of the tangent line at every point is 0. But the thing is, we call that that's a trivial function because it's just boring. It's just always 0. It's not doing anything. So e to the x is the only non-trivial function that has this property, okay? So what we're doing here today is we are talking about a new type of function called a hyperbolic trig function. And it actually has something to do with the exponential function. It turns out that in physics and engineering, different applications in chemistry, a lot of the real sciences, we seem to always get this expression that shows up, okay? And the expression that shows up is e to, oh, what am I doing? Is e to the x plus e to the negative x over 2. That seems to always kind of pop its head up out of nowhere. And then we also see e to the x minus e to the x over 2. These things just kind of seem to naturally occur in different places. And because they occur so frequently, what we did is we said, well, let's name those. Let's give those a name. And the name of these, I'm going to show you in the notes here. One of these is our hyperbolic sine, and the other one is the hyperbolic cosine. Now, for us, I want us to just take a look at this. This is e to the x. Here's e to the negative x. And so if I were to take both of those functions, go back to this. If I were to take those two functions, let's say I added them together, then all you're doing is adding the y values together, right? So imagine taking, let's say we go to 0, and we take the y value of the red one, which is 1, and we take the y value of the blue one, which is 1, and we add them together. What would we get? 1 plus 1, that's 2. And then let's take half of it, Okay, so then that would just spit out 1, wouldn't it? Okay, let's do it on, let's say we plugged in 1. We plug in 1 to the blue one, we'd be here. If we plug in 1 to the red one, we'd be here. If we add those up, we'd be, I don't know, somewhere about here. If we take half of that, we'd be about here. Okay, and we do that for all the points. Well, here's what it would look like if we graph that. I missed it a little bit there, but you see it almost looks like a parabola, doesn't it? It's not a parabola, but it almost looks like a parabola. And then I said that we also see this instead of with a plus here in the middle, sometimes we see it with a minus. So what if I do it and I subtract the 2 and then divide by 2? This is what it would look like. Okay, this orangish one. All right, so I'm just trying to get you to see that if we start out with e to the x and e to the negative x, and then either add or subtract them and divide by 2, we get these 2 new functions. And I'm telling you that those occur in the science field a lot. So we define them. Here it is. We define sine hyperbolic. So it's the sine, S-I-N, with an h next to it, sine hyperbolic of x. We define it to be e to the x minus e to the negative x over 2. Or you could pull the 2 out as a 1/2, and it's 1/2 of e to the x minus e to the negative x. That is the definition of sine hyperbolic. Now, already this is, I hope you would agree that this is already better than our definition of just sine from pre-cal. Because for us to talk about sine of x in pre-cal, well, you have to think about a unit circle, and if you want to know what sine of x is, then you're just going to have, if you want to know what sine of 2 is, you have to plug 2 into the calculator, right? Sine of 2, and your calculator does some magical stuff and gives you an answer. Here, if we wanted to figure out what sine hyperbolic of 2 is, all we're doing is plugging 2 in right here, right? So we can actually see the mechanics behind this function as opposed to the sine function. Now the cosine hyperbolic is the same thing, except there's a plus in between instead of a minus.
I have a question.
Yes.
So you said we can see the whole formula behind it. So for example, if you add a 2 in there, so what is the value of the exponential function? Like what is the value of e?
E to the 2, is that what you're saying?
Yes, e to the 2, what would be the value?
Yeah, well, we'd still have to calculate that, but e squared is just e times itself, right? So it's like 2.71 something times 2.71 something, and that's going to get, we'd have to round, of course. There would be some error in our answer because e is an irrational number, right? It keeps going forever, no pattern. We talked about this a while back. So I'm just trying to get you to see, even though we might still need our calculator to do e squared, like there's the formula in front of us. Where with sine of 2, what are you doing? You're going to your calculator, it's like a black box, right? You're just like plugging it in and it's spitting out an answer. So that's kind of a little refreshing that we have a formula for what it is. And then if we look at what the other trig functions are, they're just like they were back in pre-cal. They're just the reciprocal stuff. Well, tangent hyperbolic is just the sine hyperbolic over cosine hyperbolic. And then cosecant hyperbolic is 1 over sine hyperbolic, and secant hyperbolic is 1 over cosine hyperbolic, and so on and so forth. Now, the way that I remember it, because I'm still a student of math, but when I was learning this, I just memorized the formula, and then the way to remember the plus and minus, I just remembered like sine starts with an S, and S means subtract. I don't know, that's the way I remembered it, but however it works for you in your brain. Okay, so let's see where these functions would become useful. Okay, so let me show you an example here.
One quick thing, Professor.
Yeah.
So the 2 examples that you gave us on the graph, one of them showed a U.
Yep.
And the other one was kind of like an S. So does that only apply for sine? If you do the opposite, say instead of the curve going up, if it's down, or the other graph that you have, if it's flipped, is that a different thing or is it the same?
Well, we could make this green one that looks like a parabola, we could make it go down if we just put a negative in front of the sine hyperbolic, right? We could just make it, I'm sorry,
Okay.
the green one is the cosine hyperbolic. I should state that. The green one is the one with a plus, and the plus means cosine hyperbolic.
Okay.
So if we did negative, if I graph this negative, right, put a negative in front, then it's going to just reflect it down. I don't know if that's what you're asking me.
Yes.
Yes.
So I didn't know if that was the opposite, say like cosine instead of sine going down. And as far as the other graph that you have, the one that goes like an S, like this.
One.
Yeah. If the graph is the opposite direction, is it just matter of changing signs, or is that a different function?
No, it's just a changing of signs.
Okay.
So like in pre-cal, the sine function and the cosine function, the traditional ones, are very similar, right?
Mhm.
They're only off by a phase shift, right? Cosine and sine, you could actually lay sine on top of cosine, it'd be exactly the same if you could just move it a little left and right. With the hyperbolics, they're nothing alike, right? The sine hyperbolic and cosine hyperbolic are completely different looking, and there's no way to easily transform one to the other. Does that make sense?
Yes.
Okay. All right, so here's an example of when a cosine hyperbolic function, so I'm just going to give you one example, not going to go to all of these, but I just want you to see the value of these functions. So let's say that I take a pole, let's say I take two poles, okay, and I hang a wire between them. All right. So you have to imagine this is not like a theoretical thing. This is like a real physical situation. You have two poles and a wire hanging between them. The shape of this wire, the shape of that wire is a question mark. Like, what is it, right? Because it's kind of like gravity takes over and it just forms its own shape. And the question becomes, is that a parabola, right? Because we studied parabolas in college algebra. So our question would be, I don't know, is there some function that maybe I could find that's a quadratic, ax squared plus bx plus c? So that's what a standard quadratic looks like, right? Where if we just change a, b, and c, those are just numbers, right? If we kind of tweak those numbers, we can change the shape of the graph. Is there a way to actually create a parabola that would lay exactly on top of that wire? What do y'all think? Do you think I could tweak a parabola enough to get it to lay right on top of that wire?
Yes.
Yeah, I mean, that seems
Well,
reasonable, right? You
yeah,
have a lot of control over a parabola and how you control that, how fast it spreads, and you can move it up and down and you can reflect it. Well, it turns out that you can't, all right? There is no way to model a naturally hanging wire. You cannot model it with a quadratic function. It's impossible. You actually need a hyperbolic cosine function to do it. And so what I have here is kind of a little bit of an example. Let me make this a little bit bigger. This is just to show you that if I start out with a hyperbolic cosine function, I can control certain things on the hyperbolic cosine function. I can spread it, right? Move it up and down. I can even get it, I can get it to reflect over, but I don't think I've set this up to do it. But okay, so I can control it. Now, if I do a parabola, I can try and lay this parabola on top. Whoops. I can try my best to do this, but there's no way I can get it right on top. So
because you can't match the, I'm sorry, because you can't match the exponential part of the function because it's the only function that has that property, correct? So like trying to fix a parabola, like you don't have that same variable to like play with.
Yeah, I mean, you can get them to match up maybe at a few points, but you can't get them to match up point for point. Because one is a quadratic function, the other one is some combination of exponential functions. The thing that is, I guess, really kind of the big, like, oh, wow, I didn't know that, is that when you hang a wire, it's a cosine hyperbolic function. That's what it is. And so if you're in the engineering field and you're working with things that are suspended between 2 points, you must have hyperbolic cosine functions. You must be able to work with those, right? So you're gonna have to take that on faith that that's the way it is. All I'm trying to illustrate with this picture is that a parabola won't do. There's just no way to get them to match up. So when would we ever see something like that in the real world? So let me go back to this, this wire example, all right? So let me zoom in. Let me zoom in. Let's imagine we have that pole. Okay, here's our pole. And then we have our wire coming into this pole, all right? Okay, so think about like power lines, you know, like power electricity. You go, you drive down the road, you see these huge towers and you see these wires hung between them, right? Suspended. All of those are hyperbolic cosines, right? That's what they are. And actually there's a name for them. I should have told you this to begin with. These are called catenaries. So a catenary is a wire suspended between 2 points, all right? So you go look outside, driving down the road, you see all these catenaries, right, hanging. So electricity, right, the electrons are gonna be traveling through this wire, go from, you know, loop to loop, just down line, then they get to your house, right? Well, when this wire connects to the pole, we want to make sure that the electrons don't go through and, you know, right? We don't want the electrons to actually be able to travel and go down the pole and go straight to ground, right? That'd be a direct short. So we have to connect that wire to the pole with something that's insulated that does not conduct electricity. So we usually use, they're usually gray looking. They're like these ceramic, this is a terrible drawing, but there's these like, it's like a ceramic connector that connects to the pole. You know, if you've never seen it, just next time you drive down the road, just look up.
Yeah, they're big and brown.
Make sure you're at a stop. What?
They're big and brown.
Yeah, there's different colors to them. But you'll usually see they're made out of like some sort of ceramic or glass or something. And these things are holding these wires. Now think about this. This wire is like hundreds of feet long. So how much do you think that wire weighs, right? And it's got to be held by this ceramic holder, right? The ceramic is brittle. So they have to engineer these things very, within very tight specifications. And one of the things that they would need to know is, you know, a physics thing is what is the actual, at this point right here, where it's connected, what is the direction of that force, right? What is the direction of that force? And one of the things that we could determine or need to determine is what is that angle theta? So it's like a little, you know, here's our wire coming in and we want to know like that angle between. And the only way we're going to be able to do that is if we can look at this point and talk about the derivative of that function there, because the derivative of that function would give us the slope of the tangent line. Does that make sense? But the derivative of what function? And that's where we have to know it's the cosine hyperbolic function. All right. So this is just to show you, like, this is where this could become useful, right? You have a force, you need an angle, you need a slope. Slope means derivative. Derivative means you need the function. And we know it's the cosine hyperbolic. Okay, let's move on. So, you know, I've already shown you this. That's what sine hyperbolic looks like. This is what cosine hyperbolic looks like. Tangent hyperbolic, cosecant, secant hyperbolic, cotangent hyperbolic. So when you look at all of those, they're just all so different from one another. They're very different. If you, again, go back to pre-cal, like tangent and cotangent look really close to being the same function. They're just moved over and flipped. So we don't have those relationships here, all right? All right, so let's get to our first example, all right? The first example is an identity. We want to show that this is true. So do you remember, I'm sure you remember from pre-cal that there's an identity with sine and cosine that we use quite a bit. It's played kind of a pivotal role in our math lives. It's this Pythagorean identity, sine squared x plus cosine squared x equals 1, right? Especially back in pre-cal when you were doing identity proofs or solving equations, with trig functions. Anytime we saw sine squared x plus cosine squared x, we would get all happy because we know that turns into 1, right? Well, it turns out that with the hyperbolic trig functions, we have a similar identity, but it's not quite the same. There's not a plus between them. There's a minus, and then we know with minus or subtraction order matters. So if we take cosine hyperbolic of x and we square it, and we subtract sine hyperbolic of x and square it, we should get 1. And so right now what we're going to do is we're going to show that this is true. Okay, we're going to verify this identity. So when we verify an identity, so I'm telling you that's true, okay? Now I want you to verify it. Does anyone remember how we can verify an identity?
Using
We
the
did it in pre-cal. You always start with one side and try and turn it into the other side. Okay, so we like start with the left-hand side and do whatever algebra we can to it, and then at the end we want it to turn out to be 1. Right? What you cannot do is work with this like an equation. So like I can't add something to both sides or subtract. This is kind of like a question. Is it true? We know it's true, but we're acting like we don't know it's true. So I'm going to start with the left-hand side, LHS, left-hand side, and I'm going to see if I can turn it into the right-hand side. So I'm going to start off with my cosine hyperbolic x. I'm going to write it a little different, squared, minus my sine hyperbolic x squared. And I'm just going to keep working with this now. Now, the only thing I know is the definition of each of these. So I know that cosine hyperbolic x, by definition, is 1/2 e to the x plus e to the negative x. But I need to square that. And then minus, now sine hyperbolic x is 1/2 e to the x minus e to the negative x, and then all of that squared. So all I'm doing right now is just writing down what the definitions of those functions are, which came from these first 2 lines right here. And I should also point out that those are in your formula sheets. Okay, those, if you go to your formula sheets and you go up to right here, this is on reference page 4, hyperbolic functions. It gives you the definition of sine hyperbolic and cosine hyperbolic right here. All right, we good up to this point? Okay, now I'm going to start squaring things. And I just want to remember that there's multiplication here and multiplication here. And so I'm going to square that factor and square that factor. I'm going to square this factor and square this factor. So I should get 1/4. Now I still need to do this squaring. I haven't done it yet, but I need to square that factor. Then I have 1/4 or minus 1/4, and then I'm going to need to square this factor. All right. Now today I'm going to start off with, I think it's Rania. Am I saying that right?
Yes.
Yes?
Yes.
Okay. How are you doing today?
I'm okay.
Okay. Okay, so I'm going to ask you, Rania, to, let's take the first one. We need to do e to the x plus e to the negative x, and we need to square it, right? So we need to multiply it times itself. So let's go ahead and do this good old-fashioned FOIL. So Rania, what do we get on that first multiplication through there?
Is it e to the 2x?
E to the 2x. So you're just adding exponents, right? That's all we do here. E to the x times e to the x is e to the x plus x. Good. Okay, what about the next one? Next one's a little bit weird, Rania. What is it?
So it'd be e to the negative 2x?
You're
No.
doing e to the x times e to the negative x. So you're going to add the exponents. You can go e to the x plus negative x. And that's the same as e to the x minus x. And isn't that e to the 0?
So 1.
1.
So just
Oh,
one.
1.
It's just 1.
Right.
Rania, you got that?
Yeah, I got it.
Okay, so plus 1. Okay, let's keep going, Rania. What about the next one, the inner ones, when we multiply those? Just add up the exponents again.
So it's going to be 1.
1 again, right? We're going to get e to the 0, so we get plus 1 again. And then we'll do one more. So this one, you add up the exponents. So negative x plus negative x, e to the negative 2x. Everyone buy that? So really, when we put these together, we get this. Okay, good. Now, we got to do the other one too, right? We got to do the one that has a minus between it. So we just did this one. Now we need to do that one. So we need to do e to the x, this time minus e to the negative x times itself, e to the x minus e to the negative x. And I'll save us some time here. This will become e to the 2x minus 2 plus e to the negative 2x. So the only thing that changes in there is that you get a negative 2 inside instead of a, you get minus 1 twice. And that at the end, you'll get a minus 2. So now we're going to just put this all together over here. So I have 1/4. And then this piece here with the squared was actually this. And then this piece squared here is actually that. So I'm just going to put it all together here. E to the 2x plus 2. Oops, does everyone see I missed?
Yeah, can you put the, I was gonna say, can you put the plus in there? It's kind of bugging.
Yeah, sorry, no, that was my fault, yeah. Plus e to the negative 2x, and then minus 1/4, and then we have e to the 2x minus 2 plus e to the negative 2x. Now I'm going to distribute the 1/4 through. So 1/4 is going to go here, 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 and then minus 1/4 here, here, here. So 1/4 e to the 2x. Okay, 1/4 times 2 is a half, plus 1/4 e to the negative 2x. That's the first 3 terms, and then I distribute the negative 1/4 through, negative 1/4 e to the 2x. Negative times a negative in the middle one is going to give you a plus a half, and then a minus 1/4 e to the negative 2x. All right, is Asho around? Asho, am I saying that right?
Aisha, I'm here.
Okay, yeah, all right. I'll change it over here on my screen. I have something else, so.
Yeah, my name is accidentally misspelled, so you can call me Aisha.
Aisha, that makes sense. Okay, Aisha, so Aisha, do you see what's going to happen to that? Do you see that a lot of good things happen?
Yeah, the positive 1/4 e to the negative 2x cancels with negative 1/4 e to the negative 2x.
Okay.
It's the other one too, 1/4, that 1/4 and the other one.
Yeah, there we go. So all we're left
and then
with,
you just have 1/4.
Careful, 1/2 plus a half, right?
What's that?
Yeah.
So that's
Will
1.
be.
I think you multiplied in your head.
Oh, sorry.
Yeah.
And we can already see that through the point and in the middle there when we after the first step we take on when we're looking at the whole problem.
Mm-hmm.
So in the middle with your 1/4 where you have it highlighted, we can already make the assumption based on those signs that we're having, right? Couldn't we already go through that since we know that it's going to cancel through and that those e to the x's are going to end up already canceling out once we distribute, since we have the same value distributing for the 1/4, right?
I mean, do you feel that comfortable with it? If you do, then yeah. I mean, as long as you're confident in your own algebra, mental algebra, then sure.
Okay.
Yeah, this is just to show, you know, like where everything comes from. And I just want to make sure, the main thing on this one was making sure you understood where these ones were coming from, right? Just making sure you're comfortable with adding the exponents and things like that.
Yeah, this is a great practice for me because
Yeah,
Okay.
just to kind of get that grinding away again with these sorts of little properties. But if you're comfortable just looking at this and saying, oh yeah, this can turn into 1, then, you know, that's fine. It's really, we're just verifying the identity. That's all we're doing. So we've shown it's true, right? We've shown that this identity is true. Well, just like in pre-cal, we have a whole page of identities, right? Pages of identities from pre-cal. There's a bunch of identities that we have for hyperbolic functions, and I can't list all of them, but here are some of the important ones, all right? And I'm not gonna have you memorize those. I just want you to know they exist, okay? The one we just proved was this one, but there are others, all right? So that would be kind of a fun exercise. Like, I won't do this one, but let's just see this one right here. This one is an interesting one if we wanted to try and set it up. If I were gonna try and show this, I'm not sure who's unmuted, but I'm trying to figure out where it's coming from. Yeah, okay, is that you, Aisha? All right. All right, so if we were going to try and prove that, we'd have to start with one side and turn it into the other. So let me just show you what is this side. This side is sine hyperbolic of x plus y. So the definition of that would be 1/2 e to the what?
Is it x plus y?
X plus y. And then sine hyperbolic is the one that has a subtraction minus e to the negative x plus y. So it's kind of like whatever's in here is the part that goes into the formula, right? That's what the left-hand side would be. What's the right-hand side? This is 1/2 e to the x minus e to the negative x. This is 1/2 e to the x plus e to the negative, e to the y. Do y'all see what I'm doing? I know this is sloppy. I'm just trying to show you how you would break each side down.
Same thing, but just replace it with an x.
Yeah. And then
Same thing as the first, just replace it with the y.
E to the y minus e to the negative y. So if it were me, what I would do is I would start with the right-hand side. And I would actually like try and multiply all that together, and then start cleaning it up and hope things cancel. And at the end, I better get that. That would be a pretty good exercise.
okay.
Okay. We're not interested in all this stuff, the properties. We're interested in the derivatives, okay? We know now that there are 6 hyperbolic trig functions. We know they've got some properties. We practiced identity. We say, okay, forget that. What are the derivatives? So let's look at the derivatives, and let's look at the first one. I'm telling you that the derivative of hyperbolic sine of x is cosine hyperbolic x. That's very much like what we had in pre-cal, right? Derivative of sine of x is cosine x. So that looks good. But this one's different than what we learned before. The derivative of cosine of x is negative sine x, but hyperbolic, you see we don't have the negative on the sign, right? And then we have the rest of the derivatives, the 6 other derivatives. And I'm not going to show you all of these. I'm just going to pick one, okay? I'm just going to pick one, and we're going to prove that it's true. All right, so I'm just going to do this one. I'm going to do the derivative of cosine hyperbolic x. I'm going to show that that's sine hyperbolic x. So let's take the derivative with respect to x of cosine hyperbolic x. And let's show that that's sine hyperbolic x. So this means we want to take the derivative with respect to x of 1/2 e to the x plus e to the negative x. That's the definition of cosine hyperbolic. And now it's differentiation time. So when we take the derivative, if we have a number that's being multiplied in front, like the 1/2, that's just going to come along for the ride, right? That's what happens to constants when they're attached to the functions. They just jump on the train and come along. But then I have to do the derivative of the inside. So the first part, and let's go to Abelardo.
Yes. Abe? Yeah.
Abe, I'm going to change your name over here. Okay, Abe. So Abe, let's go ahead and take these derivatives. So you have to take derivative of e to the x, which would be?
E to the x, right?
Okay, that one's pretty clean. But what about the next one? What's derivative of e to the negative x?
Should be negative e to the x.
Negative e to the negative x.
Yes.
So you just did chain rule, didn't you? You did chain rule. You said, I'm going to take derivative of e to the negative x. So you said derivative of e to anything is itself. But then you have to take derivative of what's up there, which is
you drop the
-1,
sign.
and that's where you got the -1 from, right?
Mhm.
Good, good. Now, when you look at that, what is that? That's sine hyperbolic x, isn't
Okay.
it?
Yes.
That's the definition of sine hyperbolic x. It's 1/2 e to the x minus e to the negative x. So that just shows right there the derivative of cosine hyperbolic x is sine hyperbolic x.
Correct.
Okay, so here they are. Here are our formulas. Again, we're not going to derive each one of them. We just derived one of them. But we're going to trust that these are true. And now what we're going to do is we're going to just, what we've done now is we've added another group of 6 functions and their derivatives to our toolbox. And now we should be able to take derivatives of things and throw in, you know, all of our rules from Cal 1, product rule, quotient rule, chain rule, all of them. But now we've got these new functions to play with. Isn't it fun? We've got new functions to play with. All right, so let's take y equals x secant hyperbolic of e to the x, and we want to find the derivative of this with respect to x. So how about, is it, I don't want to say this wrong. Is it summit? Or is, am I saying that right? Summit? Or is it sumit? I don't see submit on the attendance here. Okay. How about Christian? Christian Ayala?
Yeah, here.
Hey, Chris. Chris, you go by Chris?
Yeah, usually. Yeah.
Okay, I'll go by Chris. All right, Chris. Yeah, okay, so when you take derivative of that, Chris, what do you see like as the overlying thing you have to address when you go to take derivative here?
Chain rule.
Okay, so you're seeing that where? Where are you seeing the chain rule?
With the secant.
Secant
Well, I guess,
hyperbolic.
I'm sorry. Is it product rule with
There
the
you
x
go.
first
Good.
and then chain rule after that with the secant portion?
Good job. Okay, so Chris is seeing that there's actually a product right there. You have x times secant hyperbolic of e to the x. So first thing we're going to have to do is address the product part, right?
Mm-hmm.
Now, we're going to go a little sidetrack here for a moment. Did I show you all? I feel like I didn't show you the product rule the way that I teach it. I didn't show. Did I show that to you?
Not
No.
yet.
Okay, because this is going to happen quite a bit because y'all are my Tuesday, Thursday class. I have a Monday, Wednesday class. There will be things that I can't remember if I told you guys. I think that's just me getting older. But so let's take a little side journey here before we continue with this. I want to go take a look at the formula sheet for derivatives. And I'm going to grab something here and we're going to take a look at it real fast. We'll come back to that problem. I wish I could find a way where that doesn't import as being so big. Every time I put something in here, I have to come shrink it. Okay, there are the product and quotient rules from Cal 1. So I'm going to use a slightly different notation, and let's see if we agree with this. This first product rule, is, according to the textbook, is saying that if you take f times g and you take its derivative, that it's f times g prime plus g times f prime. And then if you look at their quotient rule, they're saying if you take the quotient of two functions, f and g, then the derivative should be g times f prime minus f times g prime all over g squared. So that's the formulas according to the textbook. Now I'm going to send out a poll. Yes or no, did you learn the formulas that way? Yes or no? Like, is that the way you learned them? Okay, I think that's probably good enough. So I have about 90% of you, that's the way you learned them. And then there's only 2 people that didn't. So for the people who didn't, can you tell me how you learned it differently?
Is that you, Chris? Oh, well.
No. Didn't we learn it like that? That's how I learned it. That's how I've
No,
always.
remember he taught us ho de hi, Heidi ho.
Oh, I didn't do that. No way. Absolutely
No,
not.
that was
Okay, for the quotient rule, something
for the
like
quotient rule. Yeah. For the product rule, he told us that the order technically didn't really matter as long as there was a derivative. There was one derivative of each different function on each side.
Yeah, okay, so yeah, there's different ways to present this. So let me show you the way that I present it to my students, and then I'll explain why. And maybe you can figure out why I do it this way. So the way I do it is I say, okay, if you want to take derivative f times g, you do f prime g plus g prime f. Okay, well, what's different about that? According, mine compared to the book. I guess I switched, like I did this one over here and I did this one over here, right? And then I also commuted them. I flipped the order, right? Didn't I? Yes? Okay.
Yeah.
But it gives you the same answer. Now let's look at my quotient, the way I teach quotient. It's f prime g minus g prime f all over g squared. Okay, so what have I done?
The same thing.
Yeah, I switched that and that, okay, right? And I switched that and that, but everything else same. But now that you see them next to each other, does anyone see why I teach it the way I do?
So it's easier to remember.
How? What do you mean?
So like, for example, you have the f prime into g plus g prime into f is the same thing in the quotient law. It's just that it's divides by the g square. So it's
And
just
there's
the same.
subtraction, right?
Yeah, and the subtraction sign.
Yeah. So like when I was a student learning the product rule and quotient rule, when I looked at them, to me, they looked like really different formulas. They looked very different because like this order, the order over here has to be correct. Like you have to have the f prime and the g on the left and subtract the g prime and the f on the right. Even though this doesn't matter, it matters here. So, as I became more aware of things, I said, there's no reason why we can't switch things around. And so I always said, I'm just going to memorize this formula. And then I'm just going to remember that the quotient rule, I'm just going to change that plus to a minus and just remember to divide by g squared. Okay, that's the way my brain processed it. And that's the way I wanted to teach it and present it. Now, the reason I'm bringing this up to you is because from here on out, as I take derivatives through the rest of the class, I'm going to use the way that I just showed you. I'm not going to be using the way in the book. So I just want you to be aware of that, because if you're like, well, wait a minute, that's not the way I learned it. It's all the same. We should all come up with the same answer. But I wanted to at least justify why I do it that way. All right?
Why don't they teach it like that?
I don't know.
Sway
It makes
study.
sense, no?
Yeah,
It
it does.
makes
Yeah.
sense to do it that way, right? Because
Yeah.
if you're learning it for the first time, you're like, okay, you learn the product rule, and then all the teacher has to do is say, okay, all we're gonna do for quotient rule is change to a minus and divide by g squared. And that's a very simple thing to make the transition to.
Yeah.
Yeah, I don't know. Okay, here we go. So back to, where were we? Chris, right? Chris said we're gonna need to do the product rule. So when we do this, using the rule that I just presented to you, we're gonna be taking the derivative of the first one times the second one, plus we're gonna have to take derivative of the second one times the first one. So that's our product rule. So Chris, I'll let you take it the rest of the way. What is the derivative here?
1.
1, okay, so I'm not even gonna write it. All right, Chris, what about this guy right here?
That one is secant h e to the x times tangent h e to the x.
Okay, so very good. You'll see where Chris is using this formula right here. But for us, we don't have x, do we? We have what's inside, what's the argument of our secant hyperbolic function? It's e to the
E
x.
to the x.
Yeah, so that means that has to be replaced with e to the x, and that has to be replaced with e to the x when we apply the formula. So very good, Chris. That's negative. Somebody
Yes.
change that to a minus.
Yeah, I had already changed mine to a minus. That's why I didn't mention that. I'm sorry.
Oh, no, it's okay. So e to the x here, and then tangent hyperbolic of e to the x. All right, Chris, keep going.
And then multiply that all by e to the x.
Yes, now that's chain rule, right? So Chris had taken the derivative of the secant hyperbolic part, which gave us those two pieces, but then Chris had to go inside to the argument, take derivative of that, derivative e to the x is itself, and Chris?
And then from there, I pretty much just combined everything from there, and I factored out secant h e to the x. And then I multiplied that by...
I think you may have said this, but we also have that x there, right? Right, the product rule, we had to bring up the x that came from the original product rule, had to be tacked on to the end.
Oh crap, I missed an x. Whoops.
Okay, so you missed it, good. I mean, not good, but I'd rather you miss it than miss it on a test. So just be careful, right? You do all this great work, right, to get your nice product or your nice chain rule going there, and you get it all right, and then you forget the x, right? So just be careful. All right, and at that point, I'm happy. Okay, it's like that is the derivative. Now, could you do some work on that? Could you like factor out something and clean things up? Yeah, you could, but you're not going to get any more points or less points for just leaving it like that. All right, now if down the road we have to do something like set that equal to 0, well then yeah, you'd have to do some algebra, right? Okay, good. Make sure I mark Chris off here. All right, now, we talked about these 6 hyperbolic trig functions, some of their properties, identities, and now we know they have derivatives, and we've actually done an example of taking derivative involving them. Next up on our agenda is to figure out what the inverses of these hyperbolic functions are, right? What are the inverses? And then we'll look at their derivatives. So that's where we're headed now. So here are the inverse hyperbolic trig functions, and I'm only giving you the first 3. The other 3 are in the book, and I'm not even going to get into them. All right, they're not that important for this class. And like I said earlier, what I like about the hyperbolic trig functions is the fact that we have a nice formula for them, right? That's what we were talking about a little while ago. We actually have a formula for them. If I want to plug 2 in, I just plug 2 in here and I've got an answer. Well, the inverses, remember, are the functions that undo these, right? It undoes this function. So the inverses, let's take a look at those. Let's just look at the hyperbolic sine function, the inverse hyperbolic sine. And what do you know? There's a nice formula for it. Nice, it's not that nice, but it's, again, it's something I could plug a number in, right? If I plug a number into that, I could compute that and I can get an answer. So nice formula. Does it surprise you that there's a natural log in there? Does that surprise you?
No,
No, right? Because,
the inverse of exponential.
yeah, the inverse of e to the x is natural log of x. So it would make sense that if sine hyperbolic has e to the x in it, that its inverse, right, should have a natural log. So that's not surprising. But what we're going to do now, and this is going to be fun, is we're going to show that this is true. And this is a really, for a lot of students, this is kind of a little bit of an eye-opening exercise, because it'll require that we do something that most of you probably didn't ever do in algebra. So what I'd like to do is I'd like to break you off into groups, and I want to give you like 10 minutes. And I don't expect that you're going to figure this out in 10 minutes. What I want to see is if anyone can come up with a plan as to how to go about this. So here's what I'm really asking you to do, just so you're very clear going into your breakout rooms. We know right now that y equals sine hyperbolic of x is equal to 1/2 e to the x minus e to the negative x, right? What I'm asking you to do, and we could actually call this a function, f of x, all right, if we wanted to. What I'm asking you to do is find the inverse function of that. And your answer should be this. Okay, that's what it should be. But how are you going to show that? Like, how are you going to prove that that's true? All right, that's what I'd like for you to do in groups. Now, if for some reason you're one of those go-getters and you've already watched one of my old lectures on this and I already did it, don't go in there and like give it away, all right? If anything, you could go in there and help guide your classmates. But otherwise, I want to see if y'all remember at all from college algebra how to find inverses. And if you do, then maybe you can start attacking this and then see what sort of algebra you run into. That makes sense to everyone? Okay, I'm going to do breakout rooms. I'm going to put about 4 people in each room. I'll go 3 to 4. That way there's not too many people talking over each other. So what I want you to do is just go in there and just kind of talk about like how you would go about this. Just share your ideas. And let's say I'll give you 10 minutes. So at about, oh, go ahead.
Sure.
Yes.
You said the answer has to be what?
The answer is this right here.
Okay, got it.
Natural log of x plus the square root of x squared plus 1.
Okay, got it.
Okay. So in about 10 minutes, you'll get an alert in the room that's going to ask you to come back, and it'll give you 1 minute to come back. If you're in the room and y'all are working, y'all have a question for me, too bad, you're on your own. I'm actually not going to help you. I want you to try and just brainstorm. All right, have fun. Here you go. You're going to get invited right now. I'll see you all in 10 minutes. Okay. Well, any groups have any success?
I
think I was on
didn't.
the right track, but I didn't finish it.
I
Yeah,
feel
I
like
don't
close.
remember inverses.
Okay,
So
so
confused.
did any groups remember how we find the inverse of a function from college algebra?
First, you switch the y and the x's.
Yes, I just remember that, but I'm not too sure about how the e to the power x relates to the natural log.
Okay, so here are the steps on how to find the inverse of a function. Here, hold on, let me switch back to us here. So to find the inverse of a function from college algebra, we rewrite the function and we switch the x and y, the position, and just everywhere we see an x, we put a y, everywhere we see a y, we put an x, and then we just solve for y. So if we were to take our original function, so I guess some groups did do this, switch the x and y. Did any group get past this part and actually start trying to solve for y?
Yeah, you multiplied both sides by 2 to cancel the half, and you're left with 2x equals e to the y minus e to the negative y.
Yep, that looks good. Okay, now remember our goal is to get y equals something. So did y'all get past that?
I rewrote e to the y and e to the negative y. Like I put them in parentheses and put e to the y to the power of 1 and e to the negative, like both of them e to the y, and one of them had to the power of negative 1, and just replaced them with u's.
You did that?
Yeah.
Okay. And then you said you replaced the e to the y's with u's?
Yes.
Okay, that's interesting. Let's see. If you replace e to the y with u, then you get 2x equals u minus u to the negative 1. All right. I'm with you up to there. Is everyone following this? Okay. Did you get anywhere with that?
I know you have to put in the quadratic formula, but that's where I stopped. I didn't get anywhere past that. I went pretty slow.
Okay, good. So far, that's all correct. I think it's probably easier to see it or for everyone to see it, if you replace that u to the negative 1 with 1 over u, and then just multiply both sides of the equation by u. If we multiply both sides by u, we get this. So I multiplied left side by u, multiply the right side by u, and basically what I'm doing is clearing the fractions. Does everyone agree with that expression?
Yeah.
Yes.
Now, this is a quadratic, but see, it's quadratic that has two variables in it, u and x. Do y'all agree with that? There's two variables. So this is where things get a little weird because back in college algebra, if we have a quadratic equation equal to 0, we know how to solve this, don't we? We can say that the solutions to that equation are negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. But in college algebra, the a, the b, and the c were just numbers, weren't they? Like they were the coefficients. And the variable in the problem was the x. And so we were solving for x. Here in the problem we're looking at, what we're going to need to do is get everything over to one side. So what I really did is I moved this guy over to the right side. which made it negative, and it made the left side 0. But it's okay because I just switched the order of everything. So I just put the 0 on the right-hand side instead of the left-hand side. Y'all buy that? Now, what you have to see and what's critical right now is that, let me rewrite it one more time. We have u squared minus 2x times u minus 1 equals 0. This is a quadratic in u, meaning that the variable for us is u, right? U squared u. And the coefficients that we have are the numbers or the things that are in front. So we have a coefficient here. Our a is actually a 1. Our b has a variable in it. And our c is -1. Do y'all see that? And so we can still use the quadratic formula, except this time we're going to be solving for u, not x, right? So u will be equal to -b. What's -b for us?
-2.
Negative
2x.
2x. See, look, for us, b is everything in front of u. Everything, not just the number. It's everything in front of you, including the x. And we're taking the opposite of it, right? I'm using the formula here, the opposite of b. So it's 2x plus or minus the square root. Now, what is b squared? So what is our b here squared?
4x squared.
4x squared. Then minus 4 times a. A for us is 1. Times c. C for us is -1. All over 2 times a, but a for us is 1. So here we go. We've got u is equal to 2x plus or minus the square root of 4x plus 4, 4x squared plus 4 all over 2. We're getting there. We're getting close, actually. What we need to realize now is that there's a 4 here and a 4 here. So I can factor a 4 out of both of those terms, and that 4 can come out of the root as a what?
2.
As a 2. So I can put a 2 out here, and these 4s go away. That becomes a 1. So my next line will be, well, do y'all see that these 2s will go away? The 2, the 2, the 2?
Yeah.
So you get u is equal to x plus or minus the square root of x squared plus 1. God, we're getting really close. Look at the answer here. We're getting really close. Hold on, wrong one. This one. Right, we're getting close. We need to go back and replace u, remember? Right? Wasn't there a substitution that was made? U was e to the y.
E to the.
So e to the y equals x plus or minus square root x squared plus 1. And now if we want to get y by itself here, we need to kill off the e. So this is where we come in with the natural log on this side and the natural log on this side. So that'll leave us with y over here, natural log of x plus or minus square root x squared plus 1, close it off. Now, does that match the answer up here? Not exactly, right? Don't we have plus or minus?
Yep.
And the answer up there is just plus. So the reason why we're going to throw away the minus, and this is subtle, but it's important to understand, is that when you take the natural log of something, natural log is only defined for positive numbers. Do y'all agree with that?
Yeah.
You can't take the natural log of 0 and you can't take the natural log of a negative number. So we have to be sure that everything in here is always going to be positive. And we also need to notice that this expression right here, you'll need to think about this. Do you all agree that x squared plus 1 is always bigger than, or let's do it this way, square root of x squared plus 1. Do you all agree that's always bigger than the square root of x squared? Do you all agree with that statement?
Yes.
Right? And that's equal to x. Or you could say the absolute value of x. So what I'm getting at is this. Everything here in this like purplish reddish right here, that value is bigger than x. And you're subtracting, if we do the minus here, we're going to be subtracting that from x, aren't we? And that will give you a negative number. And so we don't want that to happen. So we have to throw away the minus. And that's how we get the original formula. So that's it. Interesting, right? This is the part right here. This is the part that I wanted everyone to see. This. The fact that you can use a quadratic formula on an equation that has the quadratic form, even if the coefficients turn out to be variables, you can still use the formula. Now your answer will have variables in it still, but the formula is still applicable to it. All right, interesting, yes? I would say?
Yes.
Okay, so now kind of last thing here in this section, we have 6 inverse functions. We just showed why it's defined this way. We could do that for the remaining ones, we're not going to, and the other 3 are in the book. Now, what are the derivatives of these, right? What are the derivatives? So we're not going to go through and derive them. We're just going to remember that they're on our formula sheets, all right? So here are the 6 inverse hyperbolic functions, and they're their derivatives, okay? And just know that they exist, all right? Just know that they exist. And that brings us pretty much to the end of 3.6. Right, so you should be able to handle that homework now. And we are ready to move on. We've still got about 20 minutes. So let's see how far we can go here. Y'all doing all right?
Yeah, as far, Professor, as far as for the lab assistants or whatever, is there better times to go and ask for help on the link that you provided?
I'm not sure what you mean.
So I know during the math hours, sometimes there's people with specialties. Is there a better time to go and ask for help for Cal 2?
I think you should ask them.
Okay.
I think that you should talk to the lab coordinator. Her name is Debbie.
Debbie.
And say, hey, you know, I'm in Cal 2. Which tutors would you recommend that I work with? And what time are they available? Because she'll know that. She'll know which tutors are good.
Okay.
Yeah. And I know, like, historically speaking, for Cal 2, there's usually just a small group that are really comfortable tutoring Cal 2. You don't really ever want to be tutored by someone who just finished the class, you know, and there's kind of like this unwritten rule that you don't want to teach math to somebody unless you have like 1 degree above what they're learning, you know? So like if you're teaching Cal 2, that's still part of an undergraduate degree, then that means you should have at least a graduate degree, you know, in math. But okay. So now we're going to start talking about antiderivatives. Now I know that for a lot of you in Cal 1, you did get into antiderivatives. And so there is some overlap here, and a lot of you have seen this already. But trust me, we're going to blow right through this beginning material. And then we're going to get into chapter 6. And then chapter 6 is when the true like meat of this course starts to develop. All right. Everything up to this point has just been like you know, hey, here's some new functions, great, we can take derivatives, we got these new things in our toolbox, and I've shown you some neat algebra. But the real challenging parts are still in front of us. So this is kind of our last, this section is kind of our last opportunity to kind of just relax. I think from here on out, it's going to be, all right, here we go. All right. So antiderivatives. We all learned in Cal 1 how to take a derivative. And with those ideas in our mind of how to take derivatives, if we were asked to go backwards, we could. So like if I put a function here, f of x equals, let's say 2x, and I asked you, hey, or I told you, hey, that's the derivative of something, okay? What is it the derivative of? Then I hope that everyone here could say x squared, right? So what I'm gonna do is I'm gonna call the place it came from capital F of x. So we have little f of x is 2x, capital F of x is x squared. Now, is that the only function that I could have taken the derivative of to get 2x? Is there another function you could think of that I could take derivative of and also get 2x?
X squared plus some random number.
Yeah, x squared plus
without a variable.
4, right? X squared, I don't know, minus pi, right? Pi is a constant. Pretty much any function I could think of, as long as it had x squared, and as long as it had a number, right? Either add or subtract a number, then all of those, if I ask you for the derivative of that, capital F, you would tell me it's 2x, right? So that's what this definition is saying right here. A function capital F is called an antiderivative, and I'm going to highlight here, an antiderivative, okay? An antiderivative of little f on the interval I if, when you take the derivative of that capital F, you get the little f, all right? That's all it means. To be an antiderivative, you just have to be able to take the derivative and get back the original function. Now, we've seen that there are basically an infinite number of answers here, aren't there? Like I could just keep going for the rest of my life. X squared plus 1, x squared plus 2, x squared plus 3, x squared plus a half from the rest of my life, and I'd never be able to write them all down. So we have something called the general antiderivative, which represents all of them, and that is x squared plus c, capital C. This is the general antiderivative. I should also make sure that you understand that when we kept on adding these numbers on the outside, that's the only thing we could do and still have the property that when we took the derivative, we got 2x. Like I couldn't have done this. I couldn't have done something other than a number. Like I couldn't have done x, right? Because when I take derivative of that, I would get 2x plus 1. So that wouldn't have worked. It has to be x squared plus a number. All right. So when you think about all the antiderivatives, all of these functions, this infinite number of functions, they all belong to a family. They all have something in common. They all look like parabolas, right? X squared. And when you add a constant or subtract a constant, all it does is moves that parabola up and down, right? That's all adding a number to a function does. So when we look at it visually, here's 2x, right? 2x is the red line. A specific example of an antiderivative is this parabola here, x squared plus 3. I could move that to x squared minus 8, and that would still be an antiderivative. But if I asked to look at, a couple of them, or maybe a few more, or a few more, or a few more, all of those belong to the family of antiderivatives of 2x. That make sense? And that would work for pretty much any function. If we have the function, this red one, 3x squared plus 10x plus 6, if we were to look for a specific antiderivative, we could get this blue one. But we could, again, have any constant, right? And so we could create a family of these. Now, on this one, I made it a little more obvious. Notice that what this family has in common is that if you move to different points on the function, just pick an x value, go to any of these curves, they all have the same slope of the tangent line, don't they? All those slopes are parallel. And the slopes are the derivatives. So that's why we're saying, doesn't matter which black one you use here, when you take its derivative, you're going to get the same thing no matter where you are. And I guess I could have illustrated that here also. Show you, there we go. Let me bring in the tangents. There we go. So no matter where I go here, all of these curves have the same derivative for a given x value. Okay, now, since this problem that we just did here, I put down 2x, and then I heard someone say, oh yeah, you know, that's the derivative of x squared. You did that just because you're experiencing Cal 1, right? You know the derivative of x squared is 2x. So that became just a mental exercise. Well, now what we can say is pretty much anything you had in Cal 1 that you were supposed to have kind of known the derivative of, we should be able to now work backwards from that. So we have a lot of common things that we should be comfortable with. So here's 1 over x. 1 over x. That's the derivative of what? Natural log, right? Natural log. So the antiderivative of 1 over x, the antiderivative of that would be natural log of x. Now they put an absolute value here, and you're going to see this from now on. And that's because natural log has a domain restriction. You can't plug negative numbers in it, so you put an absolute value just to keep your domain clean. If I wanted the general antiderivative, all I would have to do is do plus c on the end of that, and that would cover all the possible antiderivatives. The easy one, e to the x, you know that the antiderivative of that is e to the x. If I do plus c, I have all of them. Now you have to be a little careful here. The antiderivative of cosine of x, that's just sine of x. Why? Because the derivative of sine of x is cosine x, so that's pretty clean. It's this one that's a little tricky. The antiderivative of sine is not cosine, right? It's got to be negative cosine. And that's because if I were to just take the derivative of cosine, right, I would get negative sine, and that's not what I want. I'm saying what's the antiderivative of positive sine? So I'd need a negative out here in front, or a negative in front of the cosine, so that when I take derivative of it, I would get a double negative, which would turn it into a positive. Does that make sense?
So is the antiderivative actually.
Say again?
So this is the antiderivative, because
Yes.
the derivative that we learned in Cal is basically opposite.
Yep. So just to be clear, the derivative of sine of x is cosine x. The derivative of cosine x is negative sine x. The antiderivative of sine x is cosine x. The antiderivative of sine x is negative cosine x. Those are two different things. All right. And then we have more. We have more that we should recognize, right? We know that the antiderivative of secant squared is tangent. Why do we know that? Because in Cal 1, we learned that the derivative of tangent is secant squared. That's why we know that. The antiderivative of secant tangent is secant. Why do we know that? Because the derivative of secant is secant tangent from Cal 1. Okay, the next one, we learned that last class. Actually, didn't we prove that? Didn't we prove that the derivative of arc sine of x was 1 over the square root of 1 minus x squared? We actually showed that. So we should know that now. All right, and then this one, this was the one that I starred. Remember that one? Put a bunch of stars next to that one. So look, remember that one. So the antiderivative of 1 over 1 plus x squared is arctangent of x. So if we ever see this, and we want to know, you know, where that came from, that's the derivative of something, we need to know that that's arctangent. All right. Recall from Cal 1 that you learned this thing called the power rule. And the power rule said that if you have x to any power, that if you want to take the derivative, the power comes out, and then you subtract 1 from the power, right? I mean, that's one of the first rules that you learn in Cal 1. So if we have like the cube root of x, and we want to take its derivative, we first rewrite that as x to the 1/3, and then take its derivative, the 1/3 comes out, we subtract 1 from 1/3 and get 2/3. So that's all stuff that we should already be comfortable with. That was called the power rule, and now I'm going to add something to that. That's the power rule for differentiation, or for, yeah, for, I'll just say for derivatives. Well, I have good news. We have a power rule for antiderivatives too. So if somebody gives you a function that's a power function and you want to find the antiderivative, we have a rule that we can use. I know a lot of you have seen it already, but we're going to do it anyway. The power rule for antiderivatives basically has to be the reverse of the rule that we just looked at right there. So let's think about this. If somebody gives us a function, little f of x, and they say it's x to the n, and then I ask you, okay, capital F, try and figure out the antiderivative of this. What you know is that whatever this is, it's going to have to be x to a power. But the power, you know, when we take the derivative of this to get that little f, the power is going to have to reduce, right? It's going to have to come down. So that means the antiderivative, the power should be increased by 1. So instead of it being n, it's going to be n plus 1. So we're just going to add 1 to whatever this power is, right? Is that enough? Does that do it?
Plus C.
Plus c, okay, we have to do plus c. So let's try this right now. If I were to ask you right now, just take the derivative of that, what would happen?
Don't you also have to divide it by n?
Yeah, so the power would come out first, right? If I did that, if I take derivative of this, take derivative, the n plus 1 would slide out front. And then you would subtract 1 from the power. And that would give you n plus 1 times x to the n. So is that equal to this? No, right? That n plus 1 in front messes everything up. So what we need to do is in the formula, we need to account for that n plus 1. We know it's coming out, right? We know that n plus 1 is going to pop out every single time. So what we're going to do is, yeah, we're just going to divide by it. We're going to put 1 over n plus 1 in front. And that should work. And this is our power rule for antiderivatives. So let's see this in action one time. If we take f of x equals, let's just do the square root of x. Let's try and find the antiderivative of this. So the first thing we have to do is figure out what the power is here. So square root of x means 1/2. So according to the formula, the n we have is 1/2, right? So what we need to do is we need to put 1 over 1/2, that's n plus 1. Okay, so I'm just using this formula, n plus 1, x raised to the n plus 1, and then plus c. Now that's equal to 1 over 1/2 plus 1 is 3/2. And then x to the 1/2 plus 1 is 3/2 plus c. And 1 divided by a fraction is the same as the reciprocal, so we get 2/3 x to the 3/2 plus c, and we can box that up. So that's what we're saying the general antiderivative of square root of x is. Could we check this answer? How would you check it?
Just take the derivative.
Just take the derivative, right? If we take the derivative, the 3/2 would come out, and the 2/3 would kill it, right? 2/3 times 3/2 is a 1, so it's just gone. And then we subtract 1 from the power. 3/2 take away 1 is 1/2, so that would work. So this formula is very nice, and we'll have more time to practice it. But there is a problem with the formula. Does it always work? Are there any values of n where this wouldn't work?
-1.
Yeah.
If n is -1. Do y'all see that? Look at this right here. If that n right there is a -1, we get division by 0, don't we?
Yeah.
So let's just look at that special case. If we ever have, so if we have f of x equals x to the -1, our formula will not work, will it? It'll break down. But x -1 is 1 over x, isn't it? And don't we know the antiderivative of that?
Yep.
We already know it.
Natural log.
It's natural log, and we're going to start doing absolute value of x plus c. So this is the special case, right? This is that special case. So I'm going to go back to the formulas. Go back to our formula sheet. Or no. Yeah, you know what? I'll do the formulas. So we now have this right here. This page here, reference page 6, is called the table of integrals. Now, right now we haven't talked about integrals, okay? But basically an integral is an antiderivative. So when you see this symbol, it's weird, it looks like an S kind of that's been stretched out. That's called the integral sign, and we'll talk about it later. If you look at formula 2, this is basically that's basically the formula that we just had. They're writing it a little bit different, but I just want you to know, like, this sheet is going to contain a lot of formulas that we'll use as
I have a question regarding this.
we end at 240, not 46, right? I thought we ended at 245, so I'm sorry. Y'all have to stop me. Y'all just have to stop me, I'm sorry.
I have a question regarding the integrals. So are they supposed to be used in integration?
Yep. Yeah, we'll get to it. We'll get to it. We're not there yet. Y'all can bail out. You know what your homework is. I'll see you on Thursday. All right?
Thank you, sir.
Yep.
All right, thank you, sir.
Have a good day. Take
If you
care.
have any questions, I'm here. I'm not
Have a
gonna-
good day.
Real fast question. Oh.
Go ahead.
All right, thank you.
Do you want us to do like some of the antiderivative homework or
No,
not?
you can try it.
You can try it. Okay.
I know some of you have already done it, so it wouldn't hurt to just kind of brush up on it now.
Mhm.
But I'm going to do some examples next class. I'm going to work through these examples, and then I also am going to do an application, linear motion, and that'll be it. So if you wanted to, you could work on this homework. At least the first group is just antiderivative practice. So I'm sure you've seen some of this then, yes?
Yeah, my last calculus teacher, Mr. Gerwitz, he went over a little bit of integration and
Did y'all get to substitution?
I don't believe so. He told us about yeah, we were talking about in like the first day of class about like the finding the area of a graph, and then you can turn that into like a 3D image and stuff like that.
Yeah, so most Cal 1 students will see some antiderivative stuff like this, power rule, just like basic antiderivatives. And then like our next step is to go into a thing called substitution, and then integration by parts, and then trig integrals, trig substitution, partial fraction decomposition. So we've got like 5 or 6 different things we're going to do. Most Cal 1 students don't get, they just get this. I mean, sometimes I see students that have done some substitution, but nothing more than that. Minato, you've seen substitution? Is that what you're
Yes, I went over U substitution, and there was one other. I don't remember though.
Integration by parts?
I think so, but I had a question. So if antiderivatives are integrals, but by this you only mean like indefinite integrals, right?
Mm-hmm.
And so is there like a term for definite integrals where the integration is from like 0 to pi?
Mm-hmm.
It like because I have trouble with definite integrals, especially when there's like one specific I'm sorry, I went too deep.
Don't apologize. So look, let me try and answer the first part of your question. Right now, I'm using the language of antiderivatives, right?
Yes.
Because it makes the most sense to a Cal 1 student to talk about an antiderivative because you've learned about derivatives, right?
Right.
Later on, we're going to just kind of dump the whole terminology antiderivatives. Okay. And we're going to talk about integrals and indefinite integrals and definite integrals. So definite integrals, the ones you're talking about with numbers, right? That's a way that we calculate areas and volumes and things like that.
Right.
The indefinite integral is equivalent to finding the antiderivative. Those are the same. So finding the antiderivative and doing an indefinite integral are the same exact thing.
Okay.
Okay, because your answer is a function, right? Your answer is a function. When you do a definite integral, your answer is a number.
Right.
And that number has some meaning usually a physical meaning, but it could have different meanings. So those are different. So we call them definite integrals.
Okay.
Does that help?
Yes. I don't. My calculus teacher was very vague on the whole integrals thing. So.
Yeah, he went over it like really fast.
Who was it?
My calculus teacher?
Yeah.
I had Miss Peterson. I had her in high school. I just came out of high school, but I think she teaches business calculus at Northwest Vista.
Was it dual credit or was
Yes.
it an AP?
Yes, it was dual credit.
Dual credit. So the thing is, in a high school class, you probably took that Cal 1 class throughout the entire year, right?
Yes.
So I'm not surprised that you got into antiderivatives and stuff and talked about integration and definite integrals because you have 30-something weeks to do it, right? Where in a college course, we've got 16 weeks. So it's very uncommon for a college Cal 1 student to have seen definite integrals. But I can assure you that we will go through it all, and I'll be as thorough as possible. We just don't have as much time, so it will just move fast. Right now, it might seem like we're not moving that fast because a lot of the material is still familiar, maybe, but it'll start to pick up pretty quick.
Okay. Thank you.
Mm-hmm.
Random question.
Yep.
Do we ever get into differential equations and or vectors?
Do we here?
Yeah, in this class.
Mm-mm.
No. Okay.
So the book has.
Yeah, it has some stuff on it, but it's.
Okay, so the differential equations section in this book is like. Let me think of an analogy. I think I just came up. I'm terrible with analogies. It's like if I'm trying to describe to you what a circus is, okay? And I tell you elephants, man, elephants, okay? Like that doesn't fully encapsulate what a circus is.
Mm-hmm.
This one section in our book talking about differential equations is like saying elephants. it gives you no true feel or anything. This is my opinion. I don't even think it should be in the book, to be honest with you. Like it should just be its own sort of like it should be its own class, its own textbook, its own.
Well, it is its own class.
That's right. That's what I'm saying. So when you see it here, it's kind of like we can't look at that and like go through that one section and be like, yeah, I think I get these differential equations now. It's not even close. You know what I'm saying? Like it's just like a peek, just a real quick like that, and then you don't even like what was in there. It's not a fair treatment at all. And I don't think the author was trying to do that. But, you know, differential equations in general are not that difficult to understand. I mean, it's, you know, if I take an equation like x squared minus 4 equals 2, this is a quadratic equation, right? Our solutions to this are real numbers, right? So you get 2 answers, plus or minus 2, right? Okay. Now, you can have all types of equations. One type of equation you could have is an equation like this. I'll write it a little different. What if I told you I wanted you to solve this equation? It's a function equals its own derivative. Is that an equation? You see an equal sign?
Yes.
Okay, so it's an equation, right?
Yeah.
I'm asking you to tell me if you can solve this equation if you can tell me or give me an example of a function that is equal to its derivative.
E to the x.
Okay.
E to the x.
So your answer, f of x, is e to the x, works, right? So this is your solution. But your solution is not a number, right? Your solution is a function. Make sense? Does that make sense?
Oh, okay. So you're saying the answer is an equation.
You're solving for a function.
Okay.
As opposed to this, which is an equation where you're solving for a variable, which is going to turn out to give you a real number answer.
Oh,
So
okay.
Differential equations is all about solving equations that involve a function and its derivative. So you could have a function, you could have this. What if I told you solve this equation? A function that when you take that function and add to it twice its own derivative, you get 1/4 of its second derivative. You see, this is called a differential equation. It's an equation that involves a function and its derivatives. So the equation is made up of a function and its derivatives within the function, within the equation, and your task is to figure out what f of x satisfies the equation. So it's something that when you replace this, with your answer, when you take the derivative of your answer and plug it in here, and when you take the second derivative of your answer and plug it in here, you get a true statement.
Okay, so it's more like formal logic, if anything, kind of.
Yeah, it turns out that it's not easy to do differential equations in general. If they look a certain way, we have methods, but then you can get really freaking crazy and you can start doing stuff like this. Like, let me just change one thing. Instead of 2 times the first derivative, how about 2 times the first derivative squared? So now what you have is without that squared, that was called without the squared there, that was called a second order linear differential equation. Okay, second order because the second derivative is involved. Linear because nothing was being raised to a power other than 1. Now what you're looking at is a second order nonlinear differential equation. Much more difficult to solve. So the whole class is about methods to solve these things and then where they're used. Differential equations are probably the most important equations that we have out there because they relate things to their own rates of change. So you can think about you can think about like an island, just a simple example. If you have an island and you have, let's say, this is a classic example. You have foxes and you have rabbits and you've got trees and grass, right, and water, right?
Mhm.
So you've got some water here and you've got grass everywhere, right? Then if you want to talk about like populations, right? Well, if you have too many foxes, they're going to kill off the rabbits, right?
Mhm.
But then the foxes will eventually be fighting each other for food. There won't be enough food, so they'll start dying off, right? And as foxes die off, then rabbit populations start to grow again. And the rabbits can grow to a certain extent, but then they run out of grass or water, right? So, I mean, there's all these different things at play. You could always take a snapshot at like what's happening at a moment in time. But what's more interesting is trying to figure out how these populations impact one another. So if you want to talk about here, the rate at which the foxes are changing with respect to time, right, df dt, and somehow how that impacts the rate at which the rabbits are changing with respect to time, and somehow include the rate at which the grass is changing with respect to time, and the water with respect to time, then there should be some equation that somehow puts all of this together. And so as one changes, it impacts the other, right? So like, if you want to know how many foxes there are, right? How many foxes are there? That's actually a function of not only how many rabbits and how much water and how much grass, but also a function of how fast the rabbits are changing, how fast the grass is changing, how fast the water is changing, and how fast the foxes are changing. Does that make sense?
Mhm.
It's like they're all impacted, these populations are all impacted by their own rates of change. And so if you have your own rate of change in an equation, you've got a differential equation. I hope that kind of,
No, that makes more sense. Besides this, in the magnetic class I have to take.
yeah. Differential equations is a cool class. It's a little, it's always weird, differential equations, because the differences in the professor's styles with differential equations is very interesting. Like my professor for differential equations was very theoretical, really theoretical. So we were getting into like the deep underlying mathematical structure of differential equations. You can also present it in a very mechanical way, where it's like, okay, we're just trying to solve the equation, and here are the methods. Let's not talk about any of the theoretical parts. Let's just mechanically try and do it. So people often have very different experiences with differential equations. It's interesting to me how different it is. But yeah, so it's a good class. Did you ask about something else? Differential
vectors.
Vectors. So vectors, yeah, it's 10.1, I think. So here, this book talks about vectors, and all it does is it's assuming that you're comfortable with the idea of a vector being either two-dimensional or three-dimensional object, and usually numbers. So it translates over real well to physics. Mm-hmm. And we get into like dot product, cross product, things like that. Your basic vector treatment, and just a basic introduction to vectors. It doesn't go too deep.
So nothing totally practical, I guess.
Yeah, practical. Yeah, and stuff you'd see in physics and stuff like that.
Mm-hmm.
But mathematically speaking, vectors are much different. Like a vector in like pure math is very different than a vector in like the way a physics person thinks of a vector.
Because it has direction and force, I guess.
Yeah, well, so that concept of direction and force, or direction and magnitude, is a physics interpretation of a vector. But a mathematician's interpretation of a vector is not the same. Like for most people, a vector is just like a list of numbers. You know, like you have the vector 4, 3, or you have the vector like 4, 3, 1. Okay, the first one lives in 2-dimensional space. Second one lives in 3-dimensional space. Well, that's physics stuff. A mathematician understands that a vector actually doesn't even have to have numbers in here. They can be they can be any object. So they can be functions. You can have functions. So each component of the vector is a function. And then, you know how, I mean, you're talking like you know this a little bit. You can have a magnitude, right?
Mm-hmm.
The magnitude of the vector is the length of it. Well, a mathematician doesn't necessarily have to have, it's not the length of a vector, but we have to have some operation that calculates what's called its norm, okay? Which is, you could call it length, but it doesn't have to be like something you measure. It just, well, if it's a vector space, if it's a metric space, metric space means that you have a measurement on it, but not every space has to have measurement. Look, all I'm getting at is like
just different ways to interpret it, basically.
The vectors that we see in this book are part of a bigger treatment of vectors. It's not, but it's applicable. It's what you apply to physics and things like that. So definitely applicable.
Okay.
Yeah. I got to run though, guys. I've got to be somewhere at 3:30. So
Sorry.
No, it's cool. I enjoy
Sorry
talking.
for holding you up.
No, you're not.
Sorry for holding you up.
No, we'll chat again. We'll pick up this conversation later.
All right. Thanks.
Have a good one. See you Thursday.